In this last um, video on Module 3, we'll be going into different type of circuits and more details about looking at some of the other components in electrical circuits. Again, introduction to electrical circuits, and we're going to be reading schematics and diagrams and how to read using some of the symbols that you find in electrical diagrams. So in this section, we're going to be looking at how to identify the symbols um, for different types of things. So we're going to look at the symbols for a resistor and determine its value based on color codes. We're going to distinguish between series and parallel circuits. It's going a little bit deeper, and we will go a little bit more into the next section in Module 4, but looking at how these things will operate in a circuit and how the difference between series and parallel circuits. We're going to identify the instruments used to measure circuit values, voltage, current, and of course resistance. And then we're going to look at the calculate electrical power. Again, we looked at a basic circuit, has a power supply, a load, and conductors. If there's a fourth component, it will be the switch, and the switch is basically to help control the load. In other words, to turn it on and turn it off. Well, the switch, if you had a power supply, it would run forever. But using a switch, you can close it. Now, I'm sorry about the picture. It kind of blocks the schematic, but this will be an electrical diagram. In this electrical diagram, you see the power source. Let me use my marker. Okay. This is a battery. This is a single cell battery. So it's 1.5 volts. And again, we see the conductor, the load. It goes back. And this is a switch. This is electrical symbol. So this symbol here actually represents this up here, power supply. So it speeds up the process. Instead of drawing a battery out, we just draw two little lines. Matter of fact, you don't even need to put a plus or minus because this longer line means it is positive and this shorter line means that it's negative. But if we look at this, it's the light bulb, conductors, and a switch is very simple, just a straight line with two connector points, like one on this side, one on that side, with the switch in open position shows that it is not operating. There are some most of the common symbols that you may run into. I'm going to show you a few that you see all the time. Like a resistor is a zigzag line. Zigzag. This is a variable resistor. When you put an arrow through it, meaning that it is adjustable, you can change the resistance. Basically, this one here is a fixed resistor, variable resistor. And a rheostat or potentiometer is basically the same thing. It's something that you can adjust it more finely to get bring the resistance into where you want it to be. Again, a switch is a very simple device. Instead of drawing a switch out, you just draw a straight line. This is a normally open switch. If this gate was touching this point right here, it would be a closed switch. So this is open right now, and this is a switch. Other components, many times just use circles and they put letters inside of it to stand for certain things, like a motor. It might be just a circle with an M in it. Other things, like a fuse, this is a symbol of a fuse, a symbol of a ground. Let's see, this one says alternating current. Got a circle with a curved line, look like a sine wave. Other things like you see would be letters inside of the circle. These are some of the common ones you'll find. There's a lot more that you can um, that you will learn. These are different types of resistors, and it has some type of materials in it that will act as a semiconductor. It will allow current to go through it, but it restricts the flow. And it made out of different type of materials. such as carbon. It can be resistive wire. It all depends what they're trying to do. These are I'm sorry, carbon resistors. This is like a wire wound resistor using some type of wire that has resistance in that wire, and they just wrap it around many times. But again, the carbon type resistor, it is had color bands on it. You've seen electric boards, you've seen one of these because it's always would be in electrical circuits for many different reasons. Again, these are variable resistors, and again, a rheostat or potentiometer is a resistor that can adjust its resistance based on where you turn the knob. Now, how do we read the resistance of a resistor? The first two numbers is very important. There will be a color chart that will identify the color with a number. For example, some of the common numbers like or colors would be black, brown, red, orange, green, yellow. It means something. So the one the so the these bands on it usually is close to the end, and you start reading it from the closest one from left to right. So if you look at this, this will be the first band, the second band, the third band, the fourth band. The first two will tell you the number of the resistance of that band. Again, these color bands are designed by allowing you to know what the resistance of each one. So again, the first band will give you, the color will tell you the number that you're going to be using. For example, if the color is brown, the number stands for 1. So that first digit would be 1. If the second digit is black, that's a 0. And that would tell you that the second number would be 0. The third band would tell you how many um, zeros after that number, and that will give us the so it's the number of zeros in the third band, and the fourth band would tell you the tolerance, the percentage of plus or minus of that number, to say that that resistor working within a certain parameter. So again, we're going to look at this a little bit different. We can look at a chart to help determine the numbers again. So here's the chart. If we look at the chart, we see that 0, the color is black. 1 is brown. Red is 2. Orange is 3, and so forth. And here's some other ones about tolerances. If you have gold, silver, it would give you the percentage or um, of the tolerance of that resistor. Of course, this will be making it more accurate based on that color. In other words, it's closer to. In other words, you're never going to find if it's, let's say it's rated for 1,000. 1,000 would be brown, black, and it would be how many zeros? 3. So brown, black, and orange. That would be 1,000 ohms resistor. And then this would tell you either the percentage of that 5% or 10% tolerance. So again, 5% is a better resistor because it's only plus or minus 5% of is rated. If it's a silver, it's not as accurate because now it's giving you a number that the tolerance is bigger swing. It could be 10% off, either plus or minus. So again, that's looking at resistors, and it's just a way to determine um, what a resistor resistance is. Great. Now the next thing that's really important to look at is series and parallel circuits. And series and parallel circuits are two different types of way to wire any circuit. The simplest, in my opinion, is a series circuit. However, we don't use series circuits that often. A series circuit is a circuit that has a load that is in one path for current to flow. So in other words, if current is flowing this way, you only got one way to go. It goes in, it goes through, and back. It is not branching off to anything. So this is a series circuit. This middle one is a parallel circuit. You can tell these loads are in parallel. It's not one path. You got multiple paths. It's because we got different branches. We got a branch here, a branch there, and a branch there. As long as power coming in, it flows straight up. It goes this way, and so it can branch off here. The difference is that a parallel circuit is more efficient, and this is what typically we find in our wiring schemes. So again, series circuits is it's used in electronics a lot, but it doesn't work in the real world very well. Here's the reason why. In a series circuit, the voltage is shared between the two loads. So if this is 12 volts and they both the same resistance, this will receive 6 volts. This will receive 6 volts because it's sharing between the two. The rule is that a series circuit, when it comes to voltage, is the sum of the individual loads. The sum, if you add up the resistance um, or the voltage for the, let me just put it this way. If the resistance is the same for both of these, the voltage drops for each one of these will be the same. So a resistance will determine how much voltage that that load will drop. Okay, so it's important we can look at some other things as we in the classroom. A parallel circuit is different. It doesn't share, each one of them getting their own voltage. So the voltage will be the same. If there's 12 volts at the supply, this one will receive 12, this circuit will receive 12, and this circuit and load will receive 12. So now they all will, let's say if all these are the same, because we share in voltage, just these two loads only going to have less voltage. If there was a light bulb, it's going to be dim because it's only getting half what it needs. This circuit, each one of them will get the full amount of current in voltage, full amount of voltage, and it will run or glow at its fullest peak because they're getting the exact voltage it requires. Now, this is a little bit different. We'll talk more about this type of circuit. It's what we call a series parallel circuit, or a combination circuit. In this circuit here, we see that these loads, we got some parallel, like these three is in parallel, then we got these two is in series. This one is in series with these three. As it comes out, it's in series again. This circuit will react differently than either one of these two circuits. Because we have something in series with these parallel loads, whatever these two loads are dropping, it would take away from these. And so again, this is a circuit that we don't see too often. In electronics, again, you see it all the time. What do we use to measure voltage, resistance, and amperage? We have something we call a multitester, or a meter we call VOM, voltage ohm meter, volt ohm meter, VOM. And they can read amperage too, but we don't use these meters too often to read current because it's not safe to read current through. Because to read current, you have to put your meter in series with your power supply and to be able to read the current going through the circuit. And so in other words, you actually got live current going through your meter and so these probes would be hot if it slip off. It could be a live circuit touching something. So we don't use these meters too often. These are two different types. The one on the left is a digital meter. It's probably the most common meter you find today because they are accurate. They're very durable. Since there's really no true moving parts on the inside of it, there's nothing to wear out. However, The analog meter been around forever. And before they came out with digital, this was the only type of meter that we would use. And this meter is accurate. Of course, it's a lot different because you got a scale up here. You're going to have to read the right scale to get your answer of what your either resistance or your voltage or current is. And of course, you got a dial on it. You can dial it in. So this is your selector switch. Selecting, this has a selector switch too, but it's used to determine if you're reading voltage, either AC or DC, if you're reading current in amperage, or if you're reading resistance in ohms. So both of these meters can do it. Of course, this has moving parts in it, and so it can become, you have to calibrate them time to time to make sure that it is operating correctly. Now, to read current in amperage, we can use what we call a clamp-on ammeter. This becomes safe, is more safe than an analog. Here's the reason why. Um, we don't disconnect any wires like you would do with um, a digital meter. So this type of, because these jaws, it would actually sense the magnetic energy coming through the wire and convert it to amperage. Remember when I said that any wire, if there's current going through, would produce a magnetic field. These jaws would actually measure the amount of magnetic energy going through these jaws and be able to convert it to an amperage reading. So again, you do not have to remove any wires. You just clip it around one wire and be able to read the current through. Here's an example of that. They have, and plus the jaws are large enough. You can read small wires, large wires, it doesn't matter. It will be able to read it for you and very accurately. So it says do not use a clamp-on ammeter with dirty or misaligned jaws. One of the reasons why, because it can throw off through reading. It won't read a true things, especially if the jaws are open or misaligned. Use the meter on only on one conductor at a time. If you use it on two, it you're gonna actually cancel out one because one is positive, one is negative. You're gonna cancel it out, so it's not gonna read it. So again, that's why it's important that we only read one wire at a time. Okay, this is showing a analog. Well, it's not analog, it's a digital meter, but it's using a multitester VOM to read amperage. The problem, if you read amperage this way, you can see what's happening. The problem that you have here is that we never use an ohm meter to do this. It says because there's a power supply, and you could damage a meter trying to read resistance when there's power applied to it. But this is an inline amp meter. Like I say, these VOMs, they're designed to read amperage, but usually very low current. They're not designed. They will put a fuse inside of your meter, and if you read over current, it actually would blow the fuse to keep you from running or damaging the meter. Again, why it's not safe is only the reason why, because you can see this probe is touching one side, current's going through it, going to the other side, and the thing that will actually run. But the problem is, again, the safe handling of electricity. So it'd be a lot easier to leave everything connected and use a clamp-on amp meter to do it for you. Now, reading voltage is very simple. We just put our meter in parallel with the load. So in other words, if you see, it looked very similar to this when we was reading the amperage, but there's no wires disconnected. You just touch where there's a terminal someplace and be able to, on both sides of a load, to be able to determine. So again, if I put my meter on this and here on the power supply, I will read the same thing here and there, or here and there, here and there. So on both sides of the load, I will read voltage. So when you're reading voltage, the power must be on. If you're actually using your meter to read current, your meter must be on. When you're reading resistance, your power supply must be off. Your power supply. And so we go back and say this again, make sure I might have said something incorrect. When I say your meter should be on, yes, your meter should always be on. But when you're reading current or reading voltage, your power supply need to be energized. You need to be on. Now, when we're checking resistance, like I say, you must disconnect the power. Here, what you see, they put a little break right there. So they actually took the wire off or whatever, so you can actually read the resistance because you cannot have a power supply reading resistance because the battery um, inside of this meter, it is actually putting voltage through the contacts to be able to get a signal. So everything else, like reading voltage or amperage, we do need the voltage. But when reading resistance, we actually would de-energize the circuit, disconnect at least one of the leads, and then be able to read the resistance going through a switch or a wire or a coil or a motor to determine if it's is operational or not, if there is a closed circuit. So I said ohm meters can be used to check the resistance of a motor windings and to check the electrical continuity in a circuit. Continuity meaning that it is a complete path for current to flow through it. If there's anything breaking it, like a burnt out winding in a motor, something like that, it should read a different reading. It should read infinity, saying that the resistance is so high that the meter cannot read it when it's an open circuit. Here's some other tools you can use. Now, this is like a continuity tester. It's a very inexpensive way that you can use it to check continuity. Basically, use um, this tip right here, and then using this alligator clip to your one wire, and you go to the other side of the circuit to check it, and if this a light inside of it will glow, and it's saying that it's a closed circuit. If it's an open circuit, it will not. So again, this is a simple, inexpensive way to check continuity. Now, this is a voltage checker. It's inexpensive. Basically, it's not for continuity. This is actually for reading voltage to see if there's voltage. It's like I say, very inexpensive. Um, so if you cannot afford a meter at this point, you just need to know if there's voltage there or not. This device, basically, you put it on both sides of the power, and there's a little light that would glow. It's powered up from your power source. When it's low voltage, it'll be dim. When it's high voltage, it'll be bright. So again, this is a simple way. Some guys made their own by using just a light bulb and with clips on it. If it glows, it's good to go. If it don't, they know it's an open circuit. Other things that you may find calculating electrical power. Now again, power is energy, or it is what we measure in electricity, watts. Watts is a measurement of power, is a measurement of the amount of energy that you're consuming. So it's very simple. Wattage is used all the time because for the power company, the electric company, to determine how much electricity you're using, they measure it in watts. And so they have a watt meter outside. So your electrical meter is a watt meter, and it reads the amount of energy that you're consuming. So power is defined as the rate of doing work or the is the of doing work. So basically 1 watt equals 1 volt times 1 amp. So if you know what the voltage is, you know what the amperage is, you multiply them, and that would give you the amount of energy measured in watts. So again, we could look at energy in many different ways. And one thing nice about energy is convertible. from one form to another. So we can look at horsepower, which is another measurement of energy. And horsepower can be converted to electrical energy. For example, it takes 746 watts for 1 horsepower. And we can continue looking at the amount of energy that a certain amount of work can be done. So we can even convert watts into heat energy. How much energy is taken to heat something up? So again, as we look at calculating electrical power, it is always measured in, at least in the United States, in watts. This is a chart that is like Ohm's law. Matter of fact, Ohm's law is part of this chart, but it goes into a little bit deeper. It gives you every formula you can use to determine how to figure out the unknown. So again, if let's look at this, you're looking at voltage. Here's the formulas: is resistance times current, or is power divided by current, or is the square root of power times its resistance. And we can keep going through each one of these, and we'll be able to determine, even like power or watts, you can, again, it's a square of the amperage times its resistance, or again, it is voltage times its current. Either one of these, again, will give you the correct answer. But if you know 2 elements, you can determine what the third will be. Let's go over some terms. Again, we talk about amps. We know what that is. It's the current flow. So an amp meter reads current, electrical current. Kilo, that's in the metric system. And kilo means 1,000. So kilovolts, kilowatts, 1,000 watts, 1,000 volts. Mega is in the metric system again, and it's what we use for a million. When somebody says $1,000,000 or mega bucks, they're talking about $1,000,000. So mega amps, mega watts, mega volts. Ohm meter is a meter that we use to read resistance. Schematic is a type of line diagram. It's a schematic to make it easier to troubleshoot electrical diagrams. So a schematic is a type of, there's many different types of, well, not many, but there's different types of electrical diagrams, and the schematic is one of them. And the schematic is usually put into things in a parallel form where you can see everything on that one branch line was controlling that load. So it makes it easier to troubleshoot using schematics. There's other type of diagrams, such as a pictorial, which is really good when you want to know wire for wire, how to connect it. It's good, very good for that. But schematics makes it a little more difficult to wire, but it makes it easy to troubleshoot. So again, we use different type of diagrams, electrical diagrams, to troubleshoot or to wire things. A series circuit is a circuit that with only one path for current to flow. Again, it goes into one load, out of that load to the next one, to the next one, to the next one. So in other words, it is sharing um, the flow of current. So only one path. A voltage drop is where the current going through a load, when it's in series, the voltage drop uh, is divided between each of the loads. So in other words, if you have 120 volts going into the circuit and you have 3 loads equal, so each one of those would have a voltage drop of 40 volts each if it has an equal resistance. However, the sum of each one of no matter what the resistance is, the sum of each one of the voltage drop will always equals the total voltage, which is the power source. A voltmeter is a meter to measure the potential difference of a circuit, to read the force of the voltage in the circuit. Okay, we got some questions. A resistor with a gold band in the 4th position has a tolerance of, is it 1%, 5%, 10%, 20%. And if you remember looking at that color chart, it is 5%. Gold is more um, precise of a resistor than a silver band. The total resistance in a 120 volt series circuit with three 10 ohms resistor is, now I got to remember this, it shares the voltage in each, if each one of them have the same resistance, meaning that it must have the same voltage cross for each one. So if you got 120 volts, 10 ohms of resistor is 3, meaning that it's 3 times that number to equals 120. So the answer would be 30. Looked like that's a mistake they made. They're asking, oh, it's my fault. I misread the question. Say the total resistance, not amperage, or the current. So the total resistance in other words, the rule for a series circuit is, you know what? Let me just look at this. I'm going to work this out. Everybody stop for a second and see if you can work it out. Okay, I don't know if you realize this was a trick question. They threw something in there that you don't need to know. And I just assumed by looking at it. So the total resistance, that's what they're asking for in a 120 volt circuit, series circuit. Here's the thing. It doesn't matter what the voltage is. It doesn't. Because the rule that I gave you earlier is in a series circuit, it is the sum of each one of the loads. So if each of them is 10 ohms, you just add them together. So 10 plus 10 plus 10 is 30 ohms of resistance. So it was a trick question. You don't need to know at all what the voltage is to figure out this answer. Which of the following is true regarding the use of a clamp-on ammeter? A says place the jaws around a single conductor uh, at a time. B says place the jaws around an even number of conductors only. C says start at the lowest meter range and work up. And D says misaligned meter jaws can be corrected by tapping them with a hammer. Okay, of course, there's only one that is correct. So let's look at this. And I gave the answer to it. Let's see if you got it. It is place the jaws around a single conductor at a time. And that is true. Next question. Calculate the power in a circuit. Power, again, we're talking about watts. Calculate the power in a circuit where the source of 140 volts produces 10 amps. So again, you got to remember what the formula is. Your readings, you should have found out that the formula says power equals voltage times amperage. So if you multiply those two, and you will come up with the correct answer, which is 2400 watts. And we're through with the last part of unit module 3.